Hey there. I'm starting a series explaining the math behind Banan from the bottom up. No mathematical background is needed, and anyone who wants to learn can just follow along, and I will do my best to explain these concepts to be as easy to understand as possible. Banan is built on the Vulcan API. Vulcan is a new modern graphics API released by Kronos Group that efficiently uses resources on modern devices. You may suggest using another API such as OpenGL or DirectX, but both these have their own flaws. OpenGL is from 1992, and a lot has changed about graphics card architecture since then. Vulcan takes advantage of the new architecture to its fullest potential and uses GPU resources much more efficiently. DirectX is also rather old, but its bigger issue is that it's Windows exclusive, limiting the scope of Banan. Before we can even get into the math though, you first need to be able to understand how computers draw. Computers draw complex geometric shapes by dividing those shapes into triangles, as any polygon can be divided into multiple triangles very easily. So, most logically, let's first start on how computers draw triangles. On your screen, many small pixels produce a color of light to construct the images your eye sees. Think of these pixels on the screen like an area divided by square plots. To draw one triangle, we need three coordinates representing three vertices on the screen. We connect the three vertices to make a triangle, and then we can shade the area of a triangle with any color to draw our first triangle. We then plot the vertices on the screen and determine which pixels are in the bounds of the triangle. This is all done in the graphics pipeline. A graphics pipeline is exactly what it sounds like. You give an input and you get an output. The pipeline can be divided into 9 stages. However, for now, we only need 5 to draw a triangle. These stages are the input assembly stage, vertex shader stage, rasterizer stage, fragment stage, and color blending stage. The input assembly stage is a stage where we group all of our vertices into their appropriate triangles. This stage reads a vertex buffer, which is simply a list of all of our vertices. Then it groups the appropriate vertices together to form individual triangles and passes on each triangle to our next stage, the vertex stage. The vertex stage takes our triangles and applies transformations to them. This includes rotations, translations, scaling, and more. This is one of the more complicated stages that I'll have to explain fully in another video, as I use some linear algebra which I'll have to explain. The next stage is the rasterization stage. This stage breaks up the triangles into fragments in preparation for the fragment stage. Fragments are sort of like interpolated data from triangles that are used to color each pixel. This stage determines which pixels are covered by the triangles, and also which triangles are in front of each other and which ones should be rendered on top of each other. The fragment stage processes each fragment and determines what color should be outputted to the screen. This is the stage where all the major lighting calculations are done, along with the reading of textures, normals, and tangents. This will also have to be explained in another video. The final stage is the color blending stage. Fragments can appear very jagged or have some visual artifacts, so at this stage we apply methods to blend this color and fix these issues. At this stage, this is where we apply anti-aliasing. The input assembly stage, rasterizer stage, and color blending stage are all fixed function stages, meaning we as programmers have less control over these stages and can only control them through the graphics API we use. The vertex shader stage and fragment shader stages, however, give us much more control over them and allow us to upload our shader code to them, hence the word shader in their names. The majority of the math behind Banan is in these shader code stages, which we'll be going over. Now that we have a basic understanding of the graphics pipeline, we have a basic understanding of the GPU would be used in 2D computer graphics. However, for 3D computer graphics, we need to convert our 3D vertices to 2D screen space. This will all be covered in the next video about vertex shaders. In that video, we will dive deep into the vertex shader code and explain all the math of converting the 3D coordinates to 2D space. We will be using a bit of linear algebra for this, and multiplying our object space position from our vertex buffer by a set of transformation matrices to transform it into screen space. Until then though, I will continue to work on Banan and may push out an explanation video every now and then.